the last talk of this day, Laszlo Erdos, local semicircle law, and so on. Everything is written there. It's a long title, probably a very interesting talk, but not because of the length of the title.
Okay, so I'd like to thank first the organizers to invite me to give this talk here. So this is a joint work together with H.T. Yao and Benjamin Schlein. Benjamin Schlein is actually here in Cambridge, but not right now physically because he became a father this Friday, so he had to go back to take care of his newborn daughter. Now, this is a topic which in the summer in August Yao already talked about, but at that time we had weaker results. So we had results about the local semicircle law, the first part of the title, although we have improved that as well since then. And at that time we did not have Wigner estimate and level repulsion. So this is a continuation of those results. Now the key goal here is to do spectral statistics for large Wigner matrices. Wigner matrix is a Hermitian matrix with IID entries. There will be more precise definitions later on. But the important thing is that it's really IID and basically general distributions. It's not Gaussian, not necessarily Gaussian. So I'm trying to go away from the calculations which use Gaussian formulas.
Did they also work for symmetric cases too, or
yes, they work. Everything. That's right. Everything works for symmetric matrices as well. Okay, so here's the Wigner ensemble. I guess in this audience most people have seen it. Let me just fix the notation. So we take a Hermitian n by n matrix. N is always big in this talk, eventually goes to infinity. And you take a matrix whose entries are h, j, k, and they are normalized like 1 over square root of n. This is my standard normalization. So standard size, typical size of a matrix element is 1 over square root of n. You can write it as its real and imaginary part. The important part is actually the off-diagonal element, the j not equal k. There is some distribution in the diagonal element, but that matters much less in this game. And we assume that the real and imaginary part are IID random variables. We will put some conditions on these IID random variables, but explicitly we don't want to assume that this is Gaussian. Now, of course, we take some normalization, expectation 0, variance is 1/2. This is just a standard fixing the scale. So for example, of course, the Gaussian case, the GU is included, then the distribution is e to the minus x squared, the density function. Now the scaling is done in such a way that the eigenvalues of this matrix, which are denoted by nu, of course, these are real eigenvalues, we talk about Hermitian matrices, that the eigenvalues remain finite. Actually, the whole spectrum is essentially -2 and 2, maybe with a little bit tail, maybe there is some 1 or 2 eigenvalues which are a little bit bigger than that. So this you can easily check, at least roughly the size is correct, because if you compute the sum of the squares of the second moment, the sum of the squares of the eigenvalues, that's of course the trace of h squared. This is the sum of the squares of the entries, and because of the normalization, each entry is of size 1 over square root of n. So here you have a sum of altogether n squared terms. Each term is 1 over n. So that the sum is roughly n, indicating that the mu's are of order 1. So this is our chosen normalization. This is not necessarily the standard normalization. Some people like to normalize the random matrix in such a way that the entries are order 1, and then of course the spectrum is minus square root of n plus square root of n. Yes?
Don't you need some moments in order to get that result?
Yeah, there will be conditions. No,
but
there is no result
that the spectrum is between -2 and 2.
Yeah, even for that you need moment conditions.
You need more than second
moment. Sure. Yeah, sure. I mean, this is just indicating certain things. We are not, you need, yeah, sure. So here's the picture. So these are the eigenvalues. Maybe there is 1 or 2 eigenvalues beyond this -2, but essentially the bulk is inside. And also you can see that they become denser around the middle. They become less dense at the boundary. And of course, the first textual question, what you can ask is that what is the empirical density of these eigenvalues, and that leads to the Wigner semicircle law. I will formulate it more precisely later on the statement, but it's clear roughly that the middle is denser, and it's denser as the as the semicircle is higher in the middle as on the edges. Now notice also that the typical eigenvalue spacing is 1 over n. This is my choice of the normalization. There are altogether n eigenvalues in an interval of order 1. Now there are various questions which you can ask. The first one, which I already mentioned, is the density of states, or in physicist terms, this is the one-point correlation function. So for example, you can ask the following question. Take an interval about the energy E, which is somewhere inside the spectrum. That's the interesting regime, so it's between -2 and 2. And take an interval of size eta around that, symmetric interval of size eta, and then you ask yourself how many eigenvalues you have in this interval. You count them, and typically you expect, of course, something which grows with n, and moreover, so you divide the number by n, and also you divide it by the length of the interval, and you hope that you get a finite number, and this is indeed the semicircle law, explicit function depending on. Now the important thing is the order of the limits. The way how you typically formulate the semicircle law is in this order of limits. So first take n goes to infinity for a fixed interval of size eta, and after the n goes to infinity limit, you take the eta go to 0 if you want. This is the first question. This is a one-point correlation function. Much more delicate question is the n-point correlation function. This is in particular tells you something about eigenvalue spacing. What is, for example, a two-point correlation function, the relation between two neighboring eigenvalues. And this is, one can formulate it in the following way. You define the n-point correlation function. I didn't write up the definition, but I hope everybody can imagine a point process of the eigenvalues. You define the probability that you have, define the probability that around the energy E at a distance plus mu1 plus mu2 and so on, you find an eigenvalue. So you define this n-point correlation function, but it's on the scale 1 over n. So it's at a certain energy E, and then you look at distances of order 1 over n around this energy. It's a much finer object. It's a fine-tuning quantity which is designed to measure basically individual eigenvalues. And then the statement is that if you look at this one, little n is fixed, say think of little n being 2, and let n goes to infinity, then this limit eventually is independent of E as long as the energy is really inside the bulk. And it's always given by a determinant, it's an n by n matrix here, and a determinant of the famous Wigner-Dyson sign kernel. So it depends only on the mu I minus mu j differences, and you take you form this determinant for all ij. So that's the claim, and this is supposed to be very, very universal. It's supposed to be even more universal than the Wigner semicircle law. In particular, you see it's independent of the energy. This one depends on the energy, this one doesn't. So in particular, it implies level repulsion, at least in the bulk inside the spectrum, which quite explicitly for the GUE case, for the Hermitian, not the GUE, for the Hermitian case, you can write it up in the following way. You take two neighboring eigenvalues, the typical distance is 1 over n, so you multiply it by n, you get a random variable, which is supposed to be an order 1 random variable, but the probability that this order 1 random variable is of order x, where x is a small number, is damped, it decays by x squared. So that's the typical so-called Wigner surmise, that's the small distance behavior of the Wigner surmise, and the fact that it goes to 0, it's a level repulsion. This is the second question what you can ask, and the third question is, which is not directly related to the spectral statistics, is the delocalization properties of the eigenvectors. So you can ask how these are only eigenvalues, but you can ask questions about eigenvectors. I will formulate it more precisely. Now, of course, there's a universality conjecture in this whole game, namely that the local eigenvalue statistics depends only on the symmetry class of the random matrix, so whether it's Hermitian, symmetric, or symplectic, and so on. I wrote up everything for the Hermitian case, but analogous formulas are known for the other two cases. The other universality conjecture, which I think is even more interesting, especially for this community, but it's also even much more vague, is that the level repulsion and the delocalization are correlated. so in the following way, that somehow level repulsion, if you see level repulsion, that involves that occurs at the same time when delocalization occurs. This is, for the mathematics community, is not so well known. In the physics community, it's very well known. It's so much well known, to my biggest surprise, is that when numerical people, numerical physicists try to establish the phase diagram for the Anderson model, they actually identify the delocalized regime not by any of our definition, not by eigenfunction decay or something else, because these are hard to compute. They simply compute level statistics, namely they compute level repulsion, and if level repulsion is there, then they say it's delocalized regime. All these things, all these calculations rely on this completely unproven, for mathematicians at least, completely unproven conjecture. Now, of course, why we believe in that? Well, I mean, the motivation in the background is of course, comes from Schrödinger operator, where we at least have a more clear picture what it should be, how it should look like. Of course, nothing is proven here. Good. Now, there are, of course, many other motivations to study these random matrices. Now let me list first the known results, in general, first about the so-called unitary ensembles, because in this whole game, at least for me, the main difference is whether you have a unitary ensemble or not. Namely, if you have unitary ensemble, then you have explicit formulas available. Let me show you what a unitary ensemble is. So unitary ensemble is simply an ensemble, so that if you do this unitary conjugation, sandwiching between U and U inverse, then the distribution is unchanged, it's invariant. So for example, typical such ensembles are the e to the minus trace of a function of the Hamiltonian. And this is, for example, GUE. But by the way, these ensembles and the Hermish and our Wigner ensembles, these are almost orthogonal. Essentially, a typical unitary ensemble does not have, in any sense, independent entries. It's only the Gaussian case which is unitary invariant and the entries are IID. Now the big news about this guy is that you can guess immediately you can use the unitary invariance to integrate out the rotation degrees of freedom, and you get essentially a completely explicit joint density function for the eigenvalues. So you have n eigenvalues altogether. This should be a capital N here, that's a mistake. You have capital N eigenvalues and you have a joint eigenvalue distribution function which you can compute, and it has this characteristic determinant, Vandermonde determinant in it. Okay. Now, once you have this form, and there are lots of relatives of that of this idea, there's a huge community, of course, towards the orthogonal polynomials and so on. But once you have this, but all of them use such a formula, an analog of that formula. And once you have this formula, you can do quite a lot of things. In particular, you can prove the Wigner-Dyson signed kernel, which was done, I guess, first by Dyson for the GUE case, using very explicit formulas for Hermitian polynomials, and then later on, essentially, two independent proofs, one of them by Pastur and Sherbina, and the other one by Deift and collaborators with the Riemann-Hilbert approach, and probably there have been many others since then. Now the other observation is towards this eigenvector delocalization. In this particular case, and I think this was observed by Tom Spencer, the eigenvectors are delocalized in the following sense. You can compute, so Vj is the one of the j's eigenvector. You can compute its L4 norm. Eigenvectors are, of course, L2 normalized. Now, if something is delocalized, if an eigenvector is delocalized, but it's L2 normalized, it means that its entries are roughly 1 over square root of n. So then the L4 norm, or the L4 norm to the fourth power of such a vector, which is every entry of order 1 over square root of n, is of order 1 over n. So this is the way how we measure delocalization. We compute higher L3 norms. And for that particular case, the L4 norm is explicitly, very explicitly estimable. Okay, so this is what is known about unitary ensemble, but it's very important to have the unitary invariance. Now, what do you know about Wigner matrices? Well, of course, you know the semicircle law, that's the old famous paper by Wigner. You know universality at the edges. I didn't really discuss it in the previous transparencies, but there's a universality at the edge. which tells you the following. Look at the largest eigenvalue, which is a little bit above 2. It turns out that a little bit means n to the minus 2/3, so you scale it appropriately. And this quantity converges to a universal distribution, which is this Tracy-Widom distribution, which has explicit formulas and so on. And also you have similar formulas for the k-point function at the edge. Now, this is one thing which is known about towards universality for Wigner matrices, and there's another result by Johansson, who actually proved the Wigner-Dyson sign kernel in the bulk, but assuming that the entries, the matrix entries, have a Gaussian component. So it's not necessarily Gaussian itself, but it's a convolution, and the convolution contains a non-trivial Gaussian component, which, if you look at his proof, eventually ends up using similar explicit formulas that I wrote up before. And now, of course, what is open, the big conjecture, is that this Wigner-Dyson universality, especially the sign kernel, holds without any Gaussian component.
But even for the Johansson case, you need, I believe you need to be Hermitian.
Yes, sure. Yeah, everything
It will not work for the
everything is Hermitian.
everything, but you can do it for.
Yeah, okay, that's right.
That's,
yeah,
I think that's an
right.
important point.
Yeah, that's correct. I mean, what I'm going to say is true also for symmetric matrices, but his proof
And there's
is
no
not.
result by Johansson or anybody else for the.
Not
symmetric
to my
case.
knowledge.
Yeah.
When you say symmetric, it means there is no complex component.
Symmetric
Yeah,
matrix.
just real symmetric matrix.
Now here's in a nutshell our results. So all our results are for Wigner matrices under certain conditions on the decay, but not Gaussian. So first of all, we show the semicircular holds on the smallest possible scale. I will come to the precise statement in a moment. The smallest possible scale in this case is of order 1 over n, because that's the scale on which you start seeing a few eigenvalues. We prove that eigenfunctions are fully delocalized in a sense, which is the optimal result. We also studied the tail of the eigenvalue gap distribution. This is part of the so-called Wigner surmise. You look at two neighboring eigenvalues, and they are too close. It's reduced. It's damped by this level repulsion. But also you can ask yourself, what is the probability that two eigenvalues are two neighboring eigenvalues are much more far away than 1 over n. This has a decay, this has a tail, and we get a bound on that, which is sub-exponential. And we get a Wegner estimate for the average density of states. We prove that the average density of states is bounded on any scale. This is the analog of the Wegner estimate, which fortunately we have heard today in a random Schrödinger operator context from Peter. So I probably even don't have to define what it is, but it will come. And eventually we prove level repulsion for Wigner matrices. So we prove this law that the probability that two neighboring eigenvalues are closer than it should be, so close than by a small constant times 1 over n, it's proportional, it's bounded by this small constant square. So it's as strong, the eigenvalue repulsion, level repulsion is at least as strong as for the GUE. Of course, all these things are indicating the sign kernel, is consistent with the sign kernel, but we do not have the proof for the sign kernel, that's the dream. Now let me try to explain a bit more precisely the results. So first let me start with the semicircle, although this is something which Yao also explained here in August, but we have a better result now. So once more, here's the statement. This Ni is the number of eigenvalues in the interval I. You look at the number of eigenvalues in the interval of length eta about E. We divide it by n times eta once more. This is the typical number. This is the expected number of eigenvalues, what you expect in an interval of size E, the size eta. You compare it with the semicircle law, and then the claim is that and look at the probability that this deviates from what it should be, the amount of delta, and then this probability goes to 0 in this order of the limits. So you take n goes to infinity first, and then eta goes to 0. So in other words, this means the following, if you prefer this other formulation. You look at the empirical counting measure, which is just a bunch of sum of delta functions located at the eigenvalues, and then this statement tells you that this is a random measure. This converges weakly as a measure converges weakly to the semicircle law in probability. So meaning that if you test it against any fixed bounded continuous function, for example, then you get this limiting statement. Now, if you have probabilities, this is exactly a law of large number. It's a law of large number for typically order n eigenvalues, because this f is a fixed function. It typically detects order n eigenvalues. You can ask yourself what happens if the scale of the test function, let me call it eta, is actually smaller. It's not an order 1 function, but it depends on n, especially it can shrink. For example, eta is of order n to the minus alpha for some alpha power. Now, because what you expect in a scale of eta, interval of scale eta, you expect n times eta eigenvalues. You would think that the law of large numbers should still hold as long as the n times eta is bigger than 1 or much bigger than 1, because for law of large numbers, what you need more than 1. You need certain number of eigenvalues where this number sort of goes to infinity. But you certainly don't need order n eigenvalues. This is one motivation, this is one natural question: can one prove semicircle on a smaller scale? But of course it goes towards the Wigner-Dyson law as well, because the Wigner-Dyson, the sign kernel itself is of course an information, very detailed information about individual eigenfunction, eigenvalue. I mean, it basically detects for example, neighboring eigenvalues. It's on a scale 1 over n. So this is certainly a much more primitive but a preliminary question which you should be able to answer to before you try to do Wigner-Dyson law. Now here is our theorem. So it's basically what I said earlier, that we can do it on the optimal scale. Here is the way how we formulate it. Now we need some conditions, as somebody mentioned. So first of all, the distribution should have a Gaussian decay. It doesn't have to be Gaussian, but its decay has to be Gaussian. So there is at least a little delta, so that the e to the delta times x squared is smaller than it's finite. X is the distribution of a single matrix element. And also we need some symmetry condition. There are various versions of our theorems, depending how much there is a little bit trade-off between the symmetry and the decay. If you assume more decay, then you don't need symmetry. If you want to have Gaussian decay, then you need symmetry. So let me take this statement here. That this distribution is of course a distribution of complex numbers. So let me assume that it's either rotationally symmetric, the single side distribution is a complex number, or the other option is that assume that the real and imaginary parts are IID. Okay, so you need some condition like that for the distribution, and then the statement is as before. So fix an energy away from the spectral edge. This kappa is a small number which ensures me that I'm away from the spectral edge, because at the edge anyway something else is expected. And then the claim is that there is a big constant k depending only on this kappa and the epsilon. Epsilon plays the role of the threshold of the deviation. And then you look at the number of eigenvalues in this interval of length eta about e, divide by its typical number, subtract the semicircle law, and the probability that it deviates by more than epsilon can be estimated by e to the minus epsilon times the square root of n eta. And this n eta should be thought of as a big number. This means that this holds as long as n eta is bigger than this constant k. So this basically means that you have semicircle law for energy windows, which is essentially 1 over n, a big constant times 1 over n. And how big this constant should be, that depends on how precisely you want to get. So this is essentially, I think, as a scale, it's the smallest possible scale what one can hope for. And if those who remember Yao's talk in August, at that time we had a log somewhere here. So then a log was missing. Now log was too much, so now we could remove this log. And also we could get a very explicit sub-exponential bound. But those who are from large deviation theory, they may say that they don't like the square root, and they are right. There should not be square root, but there is a square root for the moment. So that the large deviation rate is not optimal. And of course, there have been many works in this, been some work in this direction, trying to prove semicircle law on shorter scale. So there was a paper by Koronji, then by Miao Tsai. They were more interested in the speed of convergence than the precise small scale structure, but these are related questions. And also about the fluctuation, there was results by Guillaume and Zaitouni. But all these results were worked on scales which were at least 1 over square root of n or bigger. And there's a reason why 1 over square root of n is easier. Okay, so now let me just flash up a little bit about the proof, and then I will come to the other results, just to indicate what's going on. Actually, everything is quite elementary here. So the main question is, the main technical tool is, of course, an upper bound to start with. It serves as an a priori estimate. So take an interval of size eta, which is at least 1 over n, and then you would like to prove something like that the number of eigenvalues in this interval, where it's expected to be n times the length of the interval times a big number k, and then this number is bigger than k times what it should be exponentially small. And here still the large deviation rate is correct. Now, so this is a natural a priori bound. You want to set that you cannot have too many eigenvalues. And the basic idea is, of course, something which has been known in this business, namely that you take the resolvent. I will always take the energy parameter Z as being E plus I times eta. E plus I times eta is the natural spectral parameter to detect what happens about an interval of in an interval of about E of size eta. So you take the resolvent, and then the imaginary part of the resolvent essentially estimates the number of eigenvalues. Standard form, and that you have to put in the etas correctly. And then, of course, it's the trace of the imaginary part of the resolvent, so you can write it up as the sum of the diagonal elements of the resolvent. And then we use the following decomposition, which is also has been used in this business several times. So how does one estimate the 1-1 element of the resolvent? Here's a decomposition of the matrix. I put it here a little bit bigger. So you separate the 1-1 element, and then the first row and the first column, and then what is left is an n-1 times n-1 matrix, which is essentially the same type of Wigner matrix, a little bit differently normalized as the big one. And then you write up the resolvent of the big matrix, n times m matrix, in terms of the resolvent of the smaller matrix. This B is supposed to be this H1 here. Now, if you know the spectrum of this H1 matrix, so in particular you know the eigenvalues and you know the eigenvectors, then you can write up everything explicitly in terms of this spectral data. And then you see that, of course, this H1 is independent of the rest. So on one hand, you have quantities which depend on H1. This U and lambda depends on H1. And on the other hand, you have the A and the H. This H11 is supposed to be H11. These are the H and A, which are independent of the U's and the lambda. So it has this independence structure. Good. And then we introduce this quantity, which naturally comes in, call it psi, which is just this dot product of the A, of this A row, the first row with the eigenvectors. This will come up all the time, and then you can write up you can write up this 1-1, or you can estimate this 1-1 resolvent element in terms of quantities which involve only these lambdas, eigenvectors, eigenvalues of that, the size, which is just this dot product, and the H. Good. Now I have to estimate it from above, because you see I had the bound. I want to estimate everything from above. I need the imaginary part of the resolvent. So I want to estimate the imaginary part by its absolute value. The absolute value I can estimate, the resolvent itself was 1 over something. I can estimate this 1 over something, by the 1 over its imaginary part. I throw away completely the real part, which is a big loss. But I'll do it for the moment. And the good news is that when you compute the imaginary part of that guy, then there is an imaginary part coming from the Z, which is this plus eta, and there's an imaginary part coming from this Z here. Everything else is real. And the two imaginary parts here help each other. They have the same sign, which is course, is known from this rank 1 perturbation formulas. But in particular, that means that you can estimate everything by a formula, which part of it comes from this z. This is this 1 after you move the eta minus 1, and the other part comes from this term. Okay, so now look at it how it looks like.
This is still a random quantity, right? This or not?
No, of course everything is random. Yeah, this is sure. I mean, I didn't take any expectation yet. I mean, it's random in many aspects. It's random. There are these lambdas, which is the n minus 1 times n minus 1 matrix. And also there is this psi, and the psi contains, as it's written here, it contains eigenvectors of h1 and this a. Okay. Now, if you look at it, how it behaves, then in here in the denominator you have a sum. You have to sum over all eigenvalues of the smaller matrix. but essentially, if you look at the formula, essentially only a few of them matters, because it's this approximate delta function type object. So actually you can estimate it, you don't lose too much. If you estimate, if within this sum, you keep only those lambdas which belong to your interval I. So you want to estimate the number of eigenvalues of the big matrix in interval I, the formula which involves all the eigenvalues of the smaller matrix, but I throw away most of them. And I don't lose too much because essentially this function is 1 over x squared plus a regularization function concentrates concentrates around the eigenvalues which are near E. Good. So now what you need, so you have this formula, you have to sum up disk size, to sum up a few of disk size, and then you need a lower bound on that, it's in the denominator. So you need a lower bound on the sum over certain size. Now what are disk size? Where size are written here, they have an IID component. A is independent of the U's, but the size themselves are not independent because each of the size is generated by the same A's. But almost, if you compute, so first of all, it's normalized in such a way that its expectation is 1, and if you compute the correlation, then the correlation is small. So it's not independent, but almost. Now the other good news, which is also well known, of course, from this rank 1 perturbation formula, that the eigenvalues of the big matrix, which was the mu's, and the eigenvalues of the smaller matrix, n minus 1 times n minus 1 matrix, which are the lambdas, they come in this interlaced form. And this is very good because here originally wanted to estimate the number of eigenvalues of the big matrix in a certain interval, and we used in the formula, we will use eigenvalues of the smaller matrix in the same interval. In principle, they have nothing to do with each other, but here they do, because they come in interlaced form. So in other words, the number of eigenvalues which you take into account here is essentially the same as the number of eigenvalues in the original interval, as the mu eigenvalues in the original interval. So you put all these things together. Of course, you still need you need a bound. Come back to that. So you need a bound on this sum. So size are almost independent, and you are fighting against them being small. So it's not really a large deviation estimate, it's a small deviation estimate. You have non-negative random variables size, and you want to show that their sum is not too big. And there are two different results. Let me just look at the first one. That's sort of the one which you would guess naturally. It's a small deviation result for sum of the size, and it essentially optimates an exponential form. Now, if you have to prove that, and if you have that, and that's where, of course, you use certain decay properties, and also use some symmetry property depending how you do it. By now, we have 3 different proofs to this fact, and they use somewhat different conditions, but the message is always the same. You have a small deviation result. And now if you put everything together, remember we estimated the number of eigenvalues. This was estimated by the sum of the diagonal elements of the resolvent, which by this rank 1 formula we could estimate, go back here, this rank 1 formula we could estimate by essentially 1 over the sum of the size. But now this small deviation result tells you that the sum of the size is essentially the same as the number of terms here. And the number of terms in this sum, this set A, is essentially the same as the number of eigenvalues because of this interlacing property. And then you have an inequality which you are very happy about because it's ni, which the quantity which you are interested in, number of eigenvalues in an interval I, is estimated by something which is 1 over ni. So then you have an upper bound on Ni, and it comes out right. Now, of course, this is a little bit hand waving. The actual proof, especially our new proof, uses a very high moment Chebyshev inequality. In earlier proofs, we had log factors. This is basically because this has swept sort of under the rug. But of course, here you had to do it for each k. I mean, it's a sum over k. All these formulas that I wrote up is only the 1 element. This little upper indices here, they always refer to the fact that it's the one coming from the 1 element. You have to do it for all of this decomposition, all of these n minus 1 times n minus 1 minors, and then you lose some, and in our old proof, at each step we lost something, and then eventually it boils down to a logarithm. But if you do everything in expectation value, in a high moment Chebyshev, then you don't have an accumulation.
Moments in, is it some of the x's or?
No, it's in this estimate. So you have this estimate, and then you take a very high moment of that.
Oh, you take a very high moment
Or
of
even
the
before
at the right hand side? Or?
Yeah, it's even here. It's even this estimate. Take a very high moment, because you see when you take a high moment of that, then in the expectation the sum disappears essentially. You take. I mean, if you want to estimate, if you want to estimate for each k, and you have a small exceptional set for each of the k's, but now you have n of them, then the exceptional sets get an extra factor n.
And you don't just take moments, you use Chebyshev.
Yeah, and if you do
cancellations in there.
yes, and if you take a very high moment Chebyshev, of course, you have to be able to take a high moment of that animal, but if you can do that, then essentially this entropy factor in the n is not, you don't pay price for that. Okay, so now this was about the upper bound. Now this was only an upper bound yet. The proof of the local semicircle law follows basically similar lines what we did, or what Yao presented in August. I don't have to spend too much time about it. Just I indicate the basic idea. This is also not I mean, that you have to look at this quantitative Stirchas transform. This is also not our idea. This has been around in the business. As you look at the Stirchas transform of the resolvent, the resolvent itself is Stirchas transform. You view the resolvent as the Stirchas transform, the empirical counting measure, and the semicircle law itself is of course the imaginary part of that. But the important thing to observe is that although you are interested in a semicircle law, it's better to look at the Stirchas transform. It's a more stable object. So it's better to look at not the imaginary part but the whole trace of the resolvent. And the semicircle law has the property that its Stirchas transform satisfies a self-consistent equation. It's a very simple quadratic equation, which that's also a defining equation of that. And the good news is that this is you can view it as a fixed point equation, and it's a stable fixed point equation, at least away from the spectral edge. So in other words, what you have M of C, this is a random object. What you are interested in, the true the Stirchas transform of the empirical counting measure. And if you can prove that this your M of C approximately satisfies this equation, then from the stability of the equation it follows that the M of C is close to the only solution to this equation. And I didn't write up more about it, but if you if you stare a little bit at this equation, I don't claim you really see it, on that side you see some term which whose sum is the resolvent itself. On the other side, or maybe somewhere here, you can see the resolvent of the n minus 1 matrix. So somehow from this equation, when you tune it up, from this equation you see an equation which looks more or less like mz plus 1 over mz plus z plus error terms. Okay, I don't want to spend more time on it because I still have to say something about the newer results. So how do you get extended states? Well, here is the result once more. Of course, there is no concept of absolutely continuous spectrum as in random Schrödinger, so the extended states really have to be understood in terms of the decay of the, or rather the no decay of the eigenfunctions. So here's the definition. a state, an L2 eigenfunction is extended if when you look at its LP norm, and P is different from 2, actually P is bigger than 2, that's the interesting regime, then the LP norm of that behaves as a certain n power, and the power here is exactly the power what you get if you plug in 1 over square root of n at each term. So for example, that was the previous result that I mentioned to the fourth moment. And I think it was Tom Spencer who asked whether this is true for general Wigner matrices. And here's our result, which essentially tells you in an optimal way. So you take an interval which is roughly which is the size of 1 over n inside the bulk of the spectrum. You fix any p, this will be the LP exponent, and then the probability that you find an eigenfunction, an eigenvector with eigenvalue in this interval, so that its LP norm is bigger than what it should be by an extra factor of m. M is a big number, is exponential or sub-exponentially small. Okay, and then this holds for a fixed interval. Now, of course, if you want to do it for all intervals, then you pick up an extra log term there, logarithmic n term, because then you have to trace all the whole spectrum. This is for finite p, and the L infinity norm is a little bit different than this m has and this m cannot be just a big number, it has to grow logarithmically. And the proof is essentially uses the same type of decomposition as before.
Does it follow from if you know the result, the final results you have for density of states, is this a corollary?
Well, I mean, I don't know what is your definition of being a corollary. It's a two-page proof after that, but the essential part is that. Now, here's the result about the tail of the gap distribution. So take again an energy inside the bulk, and suppose that mu alpha is the largest eigenvalue below the energy E. Suppose that this is not the last one. And then I look at the next eigenvalue, which is above the energy E. Look at the difference. So maybe draw the picture. So here is the E. Some energy here is the mu alpha, and somewhere here is the mu alpha plus 1. And then I'm asking about the gap. So in the way how I formatted, I ask about this distance between E and mu alpha plus 1. This is typically, I expect it to be of order 1 over n. So I look at the probability that it's much bigger than 1 over n, k times 1 over n, and the probability is smaller than e to the minus square root of k. This makes sense for large k. Now here, this is certainly not optimal. If you look at the Wigner surmise, then the expected decay is supposed to be k squared, but we don't know how to do that. And the proof is, again, I mean, depending on Tom's definition, whether it's corollary or not. So it's basically the idea is that if you have a too big gap, if two eigenvalues are too far away, then the local density of states, because now we have an information about the local density of states in a short scale, then it would mean that the local density of states in the middle of the gap is too small, and that contradicts to the lower bound on the semicircle law. You see that semicircle law has two parts, and we prove that it converges to the local density converges to a semicircle law. I showed you how to prove the upper bound. I didn't show you how to prove the lower bound, but you have a lower bound along the proof, and that comes from this self-consistent equation. And with that proof, you use, of course, the lower bound. You use that there must be some states there, and if not, then you pay for it in the probability. So this is also a believable statement that once you have a semicircle on a short scale, you can get something like that. Now let me come to the really new results. These are this is the Wigner estimate, and here you have to assume something more. I think this also showed up today in Peter's talk. You have to assume that the single side distribution at top of the decays, it's also smooth. It needs some smoothness. This is not optimal what we have, but that's what we have. So you look at the Fourier transform of the single side distribution, it has to decay at a certain rate, say t to the 10th. Now, and then you take again an energy available from a spectral edge. You take an interval I epsilon, which is about the energy E, which has a length epsilon over n. I mean, earlier I used eta for that. but now I want to use eta being epsilon over n, because now epsilon will go to 0. All the previous results were about a spectral interval of size 1 over n. I want to go even to shorter scales. And then the statement is that the probability that you have an eigenvalue in this interval of size epsilon over n is actually bounded by epsilon. And this is uniform in all parameters. So that's the key. In particular, it tells you that it cannot happen that an eigenvalue sticks to an energy. It cannot happen that for some miraculous reason there's an energy E here, and then for some reason an eigenvalue always wants to stick next to that. Which the density itself, the local semicircle would not exclude that, because the local semicircle, this distance is much smaller than 1 over n, then it's insensitive to, and doesn't show this fact. Okay, and this is of course a typical philosophy behind the Wigner estimate. And once you have that, then you can make statements about the average density of states. So you can take of course the density of state itself is a sum of delta functions on a short scale. It's a highly oscillatory, it's a widely fluctuating object, but its expectation is bounded, and it's bounded uniformly in all parameters. So it's a more precise formulation of that, but essentially the usual Wigner estimate. And unlike for this local semicircle, let me emphasize that we need smoothness on the density. And how does the proof go? We use again the same estimate what we had before. So it's the number of eigenvalues in the interval of length epsilon, and we can estimate it from above by taking the imaginary part of the JJ element of the resolvent, of the big resolvent, which we can expand it in this way, involving the eigenvalues and this size of the lower order of the n minus 1 times n minus 1 minor. So it's the same formula. This is always our basic formula what we are using. And again, we use Chebyshev to estimate the probability that there is at least one eigenvalue. In this case, it's the epsilon squared Chebyshev. So you pick up an epsilon. The epsilon comes out here, right? You pick up an epsilon squared from the Chebyshev, but then you have to compute the expectation of the square of this resolvent object. Now, earlier we had the same quantity before. When you compute the imaginary part of that, it's 1 over a complex number. You can estimate the 1 over by the complex number by just taking the 1 over the imaginary part of that. You can throw away the real part. That's what we did before. Now we cannot do that. Now you have to keep track both the imaginary part and the real part in the denominator. And it's easy to see why. So let me rewrite it in the following way. First of all, this is an expectation, which is over all the randomness. I write the expectation in such a way that it's an expectation over the lambdas and h. Lambda is this guy here, and the spectrum of the h1, and this is this little h there, and separated the expectation of these a's. These are the a's which I'm going to use. You see, every Wigner estimate has this philosophy that you need some randomness. Now, in the typical random Schrödinger, what you use is only one single randomness, and you play with that. You say that if one randomness is moving, then this randomness one single randomness kicks your eigenvalue away from the energy. Here you cannot do that. In principle, you could say that, okay, why not take, say, this diagonal element, the h11 element? That's a random object, but that's not big enough because it's of order 1 over square root of n, so it's not strong enough. You need sufficient amount of randomness, and unlike in the usual random Schrödinger case, here you have to use at least n random variables, because each random variable is 1 over square root of n. So if you use this row here, which are random variables of order 1, and we will use that to move the eigenvalue sufficiently much. Okay, so that's why we write the expectation in this way, separated the expectation with respect to A and everything else, and this is the one what we are going to play with. Good. And now let me write now where does this A appear in this formula? And the lambda and the h, these are independent of A. A appears in the psi, and psi is written here. Psi has a times the eigenvector of the smaller matrix. So this expectation over A is essentially the expectation over the psi's. Okay? So now I'm writing up everything in a form which explicitly expresses expresses the psi dependence. You do a little calculation, you compute the imaginary part and the real part here. This is the term which involves the imaginary part. I write everything in terms of a linear combination of the xi's with certain coefficients which you can compute explicitly. The coefficients involve, of course, the eigenvalue of the smaller matrix, the lambda, and here's the coefficient what you get in the real part. Now earlier, when we did the local semicircle law, we essentially used the same formula. I didn't write it up in this way, but essentially the same formula without this term. We throw away that term, we used only this term, and that was enough. But here it's not enough. If you just look at the typical sizes, then from the local semicircle law, you will know that there are certain c's which are of order epsilon, and then these two epsilons would cancel each other. I would not get anything. But on the other hand, what the local semicircle also tells you that there are certain d's. These are the coefficients which you get in the real part, which are of order 1. So the structure, the way how you should look at this object, that you have a linear combination of size, the same size, another linear combination of the same size here, and some of the coefficients here can be of order epsilon, but some of the coefficients here are of order 1. And these are the good ones, because if something, you need a big randomness. Size an order 1 object, but you need a coefficient which doesn't damp it. So let me we will just use two such c's from here and two other d's from here, and then let me just write it up in a simpler form. Of course, here you have to argue for that this is correct, but essentially the situation is that instead of this sum, you can just take two terms in the sum, and instead of this sum, you can just take two terms of the sum. These two terms have an order 1 coefficient, these two terms have order epsilon coefficient, and this is guaranteed from the local semicircle. Of course, I don't expect you that you see immediately from the formula of C and D that they scale in that way, but that's how it comes about. Now, and you have to take the expectation of that. Now, it's a dangerous object because you see it's a singular, or it may have a singularity. This guy is not quite singular because here everything is positive, but it's of order epsilon square, so it's not too strong. This guy here can be singular. That's a good one, but this may have singularity. But it's designed in such a way that if I can think of the size as being really independent random variables, namely independent complex Gaussians or squares of complex Gaussians, which is not exactly the case, but let me assume that I can think of it in that way. Then when I compute this integral here, then I get exactly epsilon minus 1. So why is that so? Well, on one hand here you have a term which is a positive term, but it's epsilon squared, and this singularity, this should be viewed as a regularization of this other singularity, which is a singularity on a surface. It's a one codimensional singularity, codimension 1 singularity, and this singularity being regularized on the scale epsilon squared. So if you're codimension 1 singularity regularized on the scale epsilon squared, its size is epsilon minus 1. And that's what you needed because from the Chebyshev you had an epsilon square, so altogether you get it. And this you need the whole real part for that. If you don't have the real part, you do the calculation, you lose the epsilon. And of course, there's a big assumption here. So we need a technical lemma which says that this is correct. Let me not read it in details, but this technical lemma tells you that whenever you compute quantities of this type, so these are very high negative powers of this kind of objects, which are like a sum of a square of a linear combination of size and another square of linear combination of size with a very high negative power, then its expectation value can be bounded by something. The explicit formula doesn't really matter. This is the number what you get if you replace all the size by independent chi-square distributed Gaussians, and then this is correct. That's the claim that although the size has some dependence in them, nevertheless, in the expectation sense, this is correct. Now, if you are a probabilist, this is none of the standard statement what you are used to. It's not a law of large number, it's not a central limit theorem, it's even not a large deviation thing. It's something about local smoothness. It basically tells you that you can think of the size as IID random variables as far as local smoothness is concerned. And the actual proof goes through by change of variables. So you have to find a good vector field along which you can integrate so that which is transversal to the singularity. I mean, for those who have seen things like that, maybe it says something. And then, of course, once you find this vector field, you do an integration by parts, and then you have to check what happens to the Jacobian. So you have to control its derivative. Now, very, very vaguely, this is actually a spectral averaging type proof, because you want to prove that the expectation where this bold face, this replaces the averaging in the spectrum, but it's just a vague statement. So here's my last theorem, and then I'm done. This is about level repulsion. So assume again some smoothness. Now fix a k. This will be the number of eigenvalues I want to say something about, say 2, 3, 5. Fix this k. I need to assume a smoothness which now depends on k. So more eigenvalues you want to trace, you need more smoothness. Again, the question is the same. What is the probability that in an interval of size epsilon over n you have more than k eigenvalues? Let me emphasize this is a tiny interval, size of epsilon over n. So typically you don't expect any eigenvalue. Okay, one eigenvalue has probability epsilon. You may think that 2 eigenvalues has probability epsilon square, 3 eigenvalue epsilon cube, and so on. That would be the case, but if you don't have any level repulsion. But what we get is that there is a level repulsion. The probability that you have k eigenvalues is epsilon to the k square. So it's much smaller, and the k square comes simply from this van der Monde determinant. So if you assume that the local statistics is really governed by the van der Monde determinant, then you get exactly the epsilon k square, and in particular for k equal to that's the level repulsion. For symmetric matrices, the exponent is different, but it's exactly the same what you expect from here, because then it's not 2 but 1. Okay, and the proof is essentially again the same formula. You start with this formula. Use the fact that you have an interlacing property. So if you have k eigenvalues of the big matrix, then you know that you have k minus 1 eigenvalues of the small matrix. Okay? And now you do the same decomposition. You take our expectation over the lambdas, which are the eigenvalues of the smaller matrix, expectation of a's, and then you are prepared to take it a high moment Chebyshev, which based upon this lemma we can estimate. And again, you find appropriate number of good indices where you can trace back what is the C and the D, and then you do an induction of K. So let me not go through it. And here's the summary. So first of all, let me emphasize again that all our results are for general Wigner matrices. We never used any Gaussian or related formulas, which are typical for the unitary invariant ensembles. And we proved that the semicircle law, should be a law, semicircle law is correct on the optimal scale of 1 over n. We proved that eigenvectors are fully delocalized, again on the optimal scale. We found the tail of the spectrum the tail of the gap distribution, which decays at least sub-exponential. This is not optimal. It should be better. We found an optimal Wigner estimate, so the average density of states is bounded, and we found an optimal level repulsion exponent, at least an upper bound. Of course, we don't have lower bounds for that. And the dream is what I said before, the sign kernel, but that's hopefully next time. Okay, thanks.
So, does this generalize to band matrices, at least in the weak sense of band being of order n? It seems it should.
Well, the result should, the proof does not.
Why? If it's independent, and I'm not talking about square root n.
Oh, you talk about really big one.
N.
Oh, n.
Yes,
n.
so that
Oh,
the profile is not constant.
You are talking about a band matrix which is, say, 1/2 n.
For example, or in general, the variances are not constant, but they change slowly.
So
For
something
example.
like that.
Yeah,
Yes.
for example.
Okay, this we haven't really
It's
thought
not
about.
semicircle. The limit law is
Yeah.
different, but there are you can write it in terms of
Yeah.
still just.
Yeah. I mean, this we checked we looked at the square root, and that
Square root is
that we don't know. And the 1/2 n maybe. I should check it, because I mean we are using lots of symmetry in a sense. We use this nice formula, which I always used at the beginning. And where is that? So we use some formula like that. And we use that the distribution of these things are always the same. So yes, I mean, okay, we should look at it. Let me say it in this way. So I mean, the 1/2 n we didn't think about. That may be doable.
But you do 1/3 n with periodic boundary conditions, so things really are the same.
I mean, 1/3 and 1/2 is.
No, 1/2 with periodic boundary conditions is the same as n.
Oh, I see. That's right. No, okay.
Okay.
But that's
So-
cheating. That's
No,
not
but
what he's meaning.
I really meant a profile, and
Yeah,
that
yeah.
should be the same technique.
Okay, we will work on it. We will try. Yes. We didn't
Because there's
have
an
any-
edge effect. If you take a 1/2 n, there's an edge effect that destroys
Mhm.
the homogeneity that you're using.
Yeah.
But if you put periodic and still made a strip, you would perhaps.
Yeah, so we
We can
keep
discuss.
we keep it in mind, but I don't want to make any claim about band matrices.
Other questions? Yes?
The localization edge close to the edge of the spectrum, is that also general for Wigner matrices?
What do you mean localization? So you ask about the eigenfunctions, how they look
Yeah.
like, or eigenvectors.
How close to the edge do the eigenfunctions get localized?
Yes.
General
We didn't look at it, so I don't know. Maybe there are some experts here who have a better guess on that. Whether Tom, do you have a
Well, I
guess?
guess I would suppose, but we don't really know that all the states are extended in some sense. But that's I've asked Soshnikov this question because actually business and all these things, but I don't think he knows. So.
No, he doesn't. I mean, I don't think his method applies.
I
to
don't
that.
think it helps. I don't think it helps. So I would not expect in ensembles that you're talking about, the big ensembles. I guess don't expect it, but I don't know. So what is the easiest of all your results? They all look very difficult. So I would have thought the Wegner estimate was the easiest, but it isn't easiest.
No, actually,
It's one of the harder ones,
the
right?
Wegner is probably the hardest. Yes, yes, because I mean the way how I presented it, it sounded relatively easy because I did this replacement. I mean, I told you that okay, this is the explicit form, and now you think of the exercise as being IID variables, but they are not. And the other thing is that this is not a this is a local smoothness result. So I mean, take for example large deviation. Either large deviation central limit theorem, if you change IID random variable to something which is slowly has little correlation, it doesn't have so much effect. But this is a small scale correlation effect. So I mean, if you do it naively, for example, just because of the correlation, just knowing that how these two sides are correlated with their correlation, it doesn't really exclude that they stick to each other on a small probability set. Stick to each other in such a way that this guy is infinite. You know, I mean, and this is 1 over a square of something. So this has a tendency to be infinite, even if on a small probability set something that happens. So they can be already infinite. So you have to exclude this, and this of course comes from the fact it's not a general effect. It comes from the fact that size have a fairly special form, and size as random variables are generated by smooth random variables. So the smoothness of the A's have to be somehow transported into the smoothness of the size. So I mean, this is the key part here. That I mean, this looks like a 3-line proof, but it's not. You have to really find a good vector field along which you integrate, and then you do all the calculation. And this vector field has to be rich enough, in some sense. As I said earlier, it has to be rich enough to involve sufficiently many random variables. See, it's the same thing in the random Schrödinger. You get Wigner estimate if you move one side. Here you have to move many sides, and and you have to move them in the right direction. So to find this direction, that's non-trivial.
Have you tried supersymmetry at all?
Yes, we did. we spent 2 months on that. You see, the problem with the supersymmetry is that once you are away from the Gaussian,
It looks nasty.
I mean, you know that, I think. And if you try to do it rigorously, then I mean, even the bosonic sector, it blows up. We tried.
So, okay. I think that some more questions. Okay. This speaker and all the speakers